Assalamu alaikum. After the introductory lecture, now we are going to formally start statistical mechanics. And our first lecture is about the Bose-Einstein statistics. So in thermodynamics, we talk about the equilibrium state. And we know that an equilibrium state is actually a state of maximum entropy. And we also know that there exists a relation between the entropy and probability. That is, a state of maximum entropy is a state of maximum probability. And this is often represented by this mathematical relation, which is sometimes known as the third postulate of statistical mechanics. So it means that equilibrium state in thermodynamics is equivalent to the more probable state in statistical mechanics. So in statistical mechanics, we talk about the thermodynamic probability of the system, and in the thermodynamic, we talk about the equilibrium state. So these are one and the same thing. Now, the thermodynamic probability of the system actually depends on the nature of the particle that make that system. And when we talk about the Bose-Einstein statistics, so this statistics is applicable to the indistinguishable particle of integral spin. Those particles are known as boson. So the boson is a family of particles who do not obey the Pauli exclusion principle. This means that there is no restriction on the number of particles occupying an energy state. So let us consider we have an energy level J which consists of two particles in the energy state 1, one particle in the energy state 2, no particle in energy state 3, and 3 particle in energy state 4. So this is the particular distribution, and this represents one of the microstate for this particular distribution. These particles are actually indistinguishable, and we represent them by the dots, but for the sake of simplicity of calculation, we temporarily assign them the tags and we represent them by A, B, C, D. So we have 6 particles and 4 energy states. So this distribution is represented by this arrangement, and this arrangement we represent by this sequence. That is, the distribution of particles among the energy state can be represented by a mixed sequence of number and alphabets. However, only those sequences that start with a number represent a possible microstate. So if we start a sequence, for example, with an alphabet, so that is meaningless. So only those sequences are representing the microstate which actually start with a number. For example, 1, 2, 3, 4, and so on. So it means that a one-to-one correspondence between a possible distribution and a sequence would give the possible number of microstates of a system. That is the thermodynamic probability. So if we associate each sequence with a particular microstate, so counting those sequences mean counting the number of microstates associated with a particular distribution. A microstate like this could be simply represented by a sequence of this type. So here we could have nj plus gj minus 1 pictorial ways of writing this sequence which start with the number 1. For example, here we have nj plus gj item, and generally we have nj plus gj whole pictorial number of ways of writing these nj plus gj items in different sequences. However, in the previous slide, we said that those sequences which doesn't start with a number, they are meaningless. So if we start this sequence with 1, so we are left with nj plus gj minus 1 item. and therefore we will have nj plus gj minus 1 pictorial ways of writing any sequence starting with the number 1. Similarly, we will also have nj plus gj minus 1 pictorial ways of writing a sequence for a distribution starting with 2, for 3, and 4 as well. So, the total number of sequences that start with a number must be equal to Gj and to Nj plus Gj minus 1 pictorial. Why Gj? Because we have Gj numbers of microstate. Here in this particular example, we have 4 microstates. So we will have 4 different sequences starting with number 1, 2, 3, and 4. However, generally, if we have Gj number of states, so we will multiply this by Gj. Now, in this sequence, we have 4 groups, each correspond to one energy state. That is, this one, this group is 1, this is 2, this is 3, and this is 4. It means that there are Gj pictorial ways of writing a sequence for a microstate. Like we can write the microstate in this sequence. We can write a microstate in this sequence. This one is starting with A, and then after A we start. This sequence started with 1, and after 1 we have 3. This sequence has started with 2. This sequence has started with 3. So you can shuffle them and Gj pictorial different ways, and all those different sequences will represent the same microstate, which is this one. So this sequence, this sequence, this sequence, this sequence actually represent this single microstate. So it means that if we have Gj and to Nj plus Gj minus 1 pictorial sequences in total, so it contains Gj pictorial sequences which actually represent the same microstate. It means in these number of sequences there are Gj pictorial repetition of the same microstate. So we have to exclude those repetition, and for that what we do, we divide the total number of sequences by the repetition. So this gives the total number of microstate for Nj particle in Gj energy state. However, if we shift or interchange some particle among the energy states, so this will give rise to new microstate. And for Nj particle, the shifting or interchange would generate Nj pictorial new microstate, because these different microstates will be generated with the shuffling of these A, B, C, D in these different sequences like this one. Now, the Nj particle are actually indistinguishable, and shuffling of the Nj alphabet would give rise to Nj new sequences, but all those sequences would correspond to the same microstate. For example, in the previous slide, the shuffling has given to this new microstate. So we have 2 different microstates which are generated because of the shuffling of A, B, C, D. However, if we consider these particle A, B, C, D as the indistinguishable and we replace them by the dot, so these 2 distribution now actually correspond to a single distribution. So when we consider the particle as distinguishable and represent them by A, B, C, D, so there are actually Nj pictorial of the new sequences. However, if these particles are indistinguishable, then those Nj pictorial new sequences actually correspond to a single microstate. So we have to exclude this repetition. For that, we divide this total number of microstates by the Nj pictorial. This means that the thermodynamic probability is equal to Gj into Nj plus 1 minus 1 pictorial divided by Nj pictorial into Gj pictorial. We can further simplify this formula by expanding Gj pictorial as Gj into Gj minus 1 factorial. So this Gj can be cancelled with this Gj, and you have this simple formula. Now we can take an example. For example, we have two particles distributed in three energy states. So according to this formula, we have to put n is equal to 2, Gj is equal to 3, Nj is equal to 2, Gj is equal to 3. So after the simplification, we have this. So it means we have 6 different possibilities of arranging two particles in 3 energy states. That is here. So here we have 3 energy states, 1, 2, and 3, and we have 2 particles. So we can put 2 particles in the energy state 1. We can put both the particle in energy state 2. We can put both the particle in energy state 3. However, we can also put one particle in one energy state and one particle in the other energy state. Similarly, one particle in the state 1, other particle in the state 3, one particle in the state 2 and other particle in state 3. So if you count this, so 1, 2, 3, 4, 5 and 6. So there are 6 possible different ways of arranging two particles and 3 energy states, and this formula gives exactly the 6th number. So it means we have calculated a correct formula. Okay, if the level is non-degenerate, it means Gj is equal to 1. So in that case, the thermodynamic probability will be equal to 1. Similarly, in the other case, if a level J is unoccupied, that is Nj is equal to 0. So in that case as well, we have omega J is equal to 1. Now, if we have a multi-level system, for each of the possible distribution in any level, there is any one of the possible distribution in the other level. This means the total number of possible distribution or thermodynamic probability of the macrostate in Bose-Einstein Statistics is equal to this. So this pi actually represents the product. So if we have a multi-level system, so the thermodynamic probability of that multi-level system in the Bose-Einstein statistics is actually the product of all those thermodynamic probability for the single level. And the thermodynamic probability of the whole system will be equal to the sum of the thermodynamic probability of the macro state. So this is the thermodynamic probability of the macro state, and this is the thermodynamic probability of the whole system. The thermodynamic probability of the macro state is equal to the product of the thermodynamic probabilities of the individual energy level, and the thermodynamic probability of the whole system is equal to the sum of the thermodynamic probability of the individual macro states. This product rule could be explained by this simple example. For example, we have two levels, E1 and E2. In E1, we have one particle and two energy states. That is, N1 is equal to 1 and G1 is equal to 2. And the second level, we have two particles and three energy states. So it we represent by N2 is equal to 2 and G2 is equal to 3. So the thermodynamic probability of this macro state will be the product of the thermodynamic probability of the level 1 multiplied by the thermodynamic probability of the level 2. So if we simplify this, so this gives rise to 12. Now, how we can obtain these 12 different macrostates? For example, In the first level, you can put one particle in the energy state 1, and then in the second level, you can put both the particle in energy state 2. Similarly, here you can have 6 different possibilities for the same microstate of the energy level E1. Now you can change this particle to here. So in the second state, we put the particle in the energy state 2. So again, for this single microstate, we have 6 microstate of the level E2. So what does it mean? We have 6 microstate here in the first row and 6 microstate here in the second row. So we have a total of 12 microstate. Mean that for one microstate there are 6 microstate, and then for another one microstate there are 6 microstate. So that is why we have a multiplication of 2 of 6, and that gives us to 12. That is, there are 2 possible microstate for the energy level E1 and 6 possible state for the energy level E2. So that is why we multiply the 2, and this gives us the total number of the microstate for this particular macrostate, which consists of the 2 energy level. Now, if we take a more general example where we have a total number of particles is 6 and the total energy is 6 epsilon, and we have 7 energy level, and each energy level has a degeneracy of 3. It means that each energy level has 3 energy states. So here we have to distribute 6 particles among the various energy level so that the total energy of the distribution does not exceed 6. This is the condition on the distribution. So for example, uh, these horizontal rows, they represent the energy level, and each energy level has energy. For example, this is the 0 energy state, this is the 1, this is the 2, this is 3, and so on. And these vertical column represent the macro state. So if we start filling these energy level with the 6 particle in order to obtain 6 unit of energy, so we put one particle in the energy level 6. So now the total energy is completed, and we have to put rest of the particle in the 0 energy level. If we put one particle in the energy level 5, so now we have to put one particle in energy level 1, so that the total energy of these 2 particles is 6, and we have to put the rest of the 4 particle in the 0 energy level. If we put one particle in energy level 4, so one particle in energy level 2, one particle if in the energy level 4, so 2 particle in the energy level 1. So one particle has 1 energy, other particle has 2 energy. So 2 unit energy and 4 unit energy is 6, and rest of the 3 particle in the 0 energy level. Similarly, 2 particle energy level 3 gives 6 unit of energy. So rest of the particle in the 0 energy level. Similarly, one particle in the energy level 3, one particle in the energy level 2, and one particle in the energy level 1 gives rise to 6 unit of energy. So we put rest of the particle in the 0 energy level. Similarly, one particle in the energy level 3 and 3 particles in the energy level 1 give 6 unit of energy. So put rest of the 2 particles in the 0 energy level. Similarly, 3 particles in the energy level 2 give rise to 6 unit of energy. So put rest of the 3 particles in the 0 energy level. Similarly, 2 particles in the energy level 2 and 2 particles in energy level 3 give 6 unit of energy. So we put rest of the 2 particles in the 0 energy level. 1 particle in the energy level 2 and 4 particles in the energy level 1 give 6 unit of energy. So put the final one particle in the zero energy level. Similarly, if we put all the 6 particles in the energy level 1, so it gives rise to 6 unit of energy. So we put no particle in the zero energy state or no particle in the upper energy state, and the total energy of these 6 particles in the energy level 1 is 6. So here we can calculate the thermodynamic probability or the number of microstate corresponding to each macrostate. So for the macrostate k is equal to 1, the thermodynamic probability is 63, and this is calculated using this formula of the Bose-Einstein statistic. Similarly, the thermodynamic probability of the macrostate 2 is 135, 135, 180, 90, and so on. And now this is the total number of microstate or the thermodynamic probability of the system calculated using this formula. If you look into the thermodynamic probabilities of these different macrostate, so we see that some macrostate have higher probability and some macrostate have lower probability. For example, the highest probability is this one, 270. This means this is the most probable macrostate, and the most probable macrostate actually represent the equilibrium properties of the system. If we calculate the average occupation number of this level 2, so we use this formula, and this comes out to be 0.83, which could be nearly equal to 1. So we see that in the energy level 2 of the most probable macrostate, the particle is 1, which is quite close to the 0.83. So this slight difference is because we have just considered a very small number of particles, 6. If we consider more number of particles, so the difference will become very, very small. So this is all about the thermodynamic probability by using the Bose-Einstein statistic. So if I summarize the today presentation, so the thermodynamic equilibrium state is represented by the most probable state in statistical mechanics. The thermodynamic probability depends on the nature of particle. In Bose-Einstein statistics, this applies to the system of indistinguishable boson, and distribution of particle among the available energy state constitute a microstate. And a microstate is represented by a sequence of numbers in alphabet, and the number of sequence could be associated with the number of microstate. That is, the total number of sequences representing the total number of microstates is equal to the thermodynamic probability. And the thermodynamic probability of an energy level with Nj particles distributed in Gj energy state is given by this formula. And the thermodynamic probability of the macrostate consisting of J levels is given by this formula. So this was all about the Bose-Einstein statistic, and the next lecture will be about the Fermi-Dirac statistics, which is applicable to the fermion, and fermion are the particles which obey the Fermi-Dirac, which obey the Pauli exclusion principle.